Hello, everyone. This is Sadoghi from UC Davis. It's excited to be here along with my students at Expo Lab. And what we're going to talk about is our experience basically around blockchain over the last few years. This is tutorial has been evolved. We have the initial version of this was given at middleware 2019, and then we also give an this year at Depth 2020. So this is the third iteration of this tutorial that not only covers the existing approaches in the last 10, 20 years, but also covers some of the recent work that we have done. And so the way we're going to do this tutorial, first Jelle Hellings, my postdoc, is going to talk about the theoretical aspect of the blockchain. And then we move to the second session, and Suyash Gupta is going to talk about uh, the state of the art or the modern algorithms, modern consensus protocols. And then finally, Sajjad Rahnama, also my PhD student, he's going to talk about, again, some of the recent work that we have done in this space on global consensus, and also on how do we build and how do you architect a blockchain fabric. And then we're also going to cover a hands-on tutorial of ResilientDB, which is the in-house blockchain that we've developed starting January of 2018. So with that, very excited about this. And so let's get started.
Welcome to our tutorial about high-throughput permission blockchains. My name is Jelle Hellings and I will introduce this topic and give some theoretical background. First things first, we are the Exploratory Systems Lab at the University of California in Davis, and we work as a lab on achieving high-performance resilient data processing. That's our end goal, and we work on that with one professor, one postdoc, 3 PhD students and a few master and bachelor students. Some of this work has already been published, but there's still a lot of results coming up soon. And if you look close at what we're doing, we really focus on combining, on intersecting blockchain technology, which provides resilience, and database technology that provides high performance. And some of this work already led to a real-world fabric that you all can already use called ResilientDB. And this fabric already is pioneering quite a few new data platform technologies. But next, of course, if I say that our goal is to achieve high performance resilient data processing, then you can ask yourself why and how that relates to blockchains. And of course, if those questions are answered, what do we already have to achieve high performance resilient data processing? Where can we improve and where can we do our research? And what new tools do we figure out that we need to develop? And in this introduction, I will answer each of these questions. So first the why, and the why is really simple. On the one hand, we want resilient data processing because data processing that can handle with crashes, that can handle with failures, with malicious behaviors, of course, always preferable over data processing that cannot do that. And this can already be seen in standard databases. Where standard databases provide consistency of data, even if crashes happen, they can recover data without losing it. If that's your basic assumption, then of course one step further is that crashes can happen without even affecting service. So if something crashes, I can still send my transaction and get results. And we want to go even one step further, namely we want to be able to deal with malicious behavior of parts of our system. And that malicious behavior can be due to attacks, but that can of course also be due to some replicas or some parts of the system being misconfigured or being unavailable or that kind of stuff. And by enabling this kind of Byzantine resilience, we also hope to enable new types of applications, for example, applications that can provide services during failures, during attacks, on the one hand, and on the other hand, applications that thrive in a federated environment in which many different participants contribute together to managing the data. And of course, in such a diverse environment, you will see that some participants will sometimes make errors configuring the systems, will disconnect from the network, and we need to be able to deal with that. And Byzantine resilience is a nice framework that can help achieve that. Then of course the other question is why we want high performance. And I think we all know that we need high performance just to be able to support future data applications. Because on the one hand, we see that there's an ever-growing volume of data, for example, coming from sensor networks. And on the other hand, we see that there's an ever-growing demand of applications for computational power, for analytics, and for example, if you want to apply machine learning. So high performance for data processing is a given, and we want to add on top of that resilience. Having said all of that, the question that of course is directly on your mind is how does it relate with blockchains, because blockchains is of course the topic of this tutorial. I will look at that next. And before we go into depth in that, we first have to determine what a blockchain actually is. And one way to do that is to say, okay, let's look at the first blockchain, namely Bitcoin. And Bitcoin was designed to manage monetary tokens called Bitcoins. And these monetary tokens, of course, represent some value. And if you want to manage those, then of course you need a way to transfer tokens from one owner to another owner. And these are just your basic transactions. And Bitcoin wants to allow processing of these transactions in an open and decentralized manner. So anyone can participate in the process and can stop or join at any given time without any other requirements. Well, the Bitcoin network itself doesn't really hold accounts with amounts of tokens. No, they just keep track of the full order of transactions that has happened in the past, and from that one can determine how much one owns at this point. And this full history of transactions is called the ledger, and it's stored in a very special data structure, namely the blockchain. And the blockchain, it's a chain, it has a starting point, some genesis value, in this diagram that's V. And after the genesis value come blocks, and each block holds a pointer to the previous value in the form of a hash. It holds a puzzle that helps in the construction of the block in a way that's secure, and it holds a whole set of transactions. And of course, having such a sequence of blocks indeed represents a history of transactions. In Bitcoin, because it's open and decentralized, there are many participants that hold a full copy of this blockchain. And the blockchain structure itself is designed in such a way that it cannot be changed, but it can be appended on. Of course, cannot be changed is absolute, but it's made very hard to make changes, even though it's quite easy to add new blocks. And to see why it is so hard to make changes, we look at some basic malicious behavior, namely a malicious agent that wants to replace one transaction by another transaction that is better for him. We do that in this case by changing a block B2. We want one transaction in that block to be removed and replaced. And anyone can do that by just making a new second block that points to the first block and say, okay, this I think is the next part of the chain. Now, how do we prevent such an attack? Well, in blockchain, all good participants have an incentive to always accept the longest chain they are aware of. So in this case, if you're already aware of block B4 and you see this block B2 prime, you say, okay, I'm just going to ignore it because it's short. But of course, what a malicious attacker can then say, okay, I have this B2 prime, I'm just going to make a B3 prime, a B4 prime, and a B5 prime, so that this changed malicious attack is the longest chain. And Bitcoin prevents this by requiring each block that is made to also solve a puzzle, and this puzzle is really costly to solve. And of course, all good participants are at the same time as the attacker also solving puzzles, but then for the longest chain. So the attacker really needs to control a lot of the participants to be able to make a longer chain himself. And so in practice, we typically just see that a malicious attempt to change a block will just lead to a dead end. And in this way, Bitcoin really prevents malicious behavior that inadvertently wants to change the chain. So, abstracting a little bit away from the setting of the Bitcoin blockchain, we can ask ourselves again, what is a blockchain? And in its basic, it's just a resilient and tamper-proof ledger that's maintained by many participants. So in the ledger, It's just an append-only sequence of transactions, and in database terms we call that a journal or a log depending on the setting. The resilience really points at that there's high availability, so there's full replication of this blockchain among all participants, and if a few participants fail, we still have access to the blockchain. And the tamper-proof nature comes from that participants can only make changes if there's a majority vote for doing so. So it's very hard to change decisions that have been made. And in this sense, blockchains are just distributed, fully replicated systems. And that's a good thing because we know quite a bit about these systems. Now let's look a little bit further. So if we would have a blockchain system, it's of course not just a blockchain, it's a system. So what does it comprise of? Well, first we have replicas, and these replicas each hold the ledger or the blockchain, and this ledger is just a sequence of transactions. We also have clients, and these clients want to process new transactions, propose new transactions. And if a system receives such a new transaction, then of course all replicas have to decide to either execute that transaction or ignore it. So how they do that? By reaching agreement on the transaction via consensus protocol. And finally, of course, if agreement is met, then the transaction is appended to the ledger at each of the replicas, and the blockchain has, well, basically executed a new transaction. Of course, a last component that's also part of this is a whole lot of cryptography to secure against malicious behavior and to make sure that transactions come from clients and all that kind of stuff. Well, of course, like I said, initially our work is about permissioned blockchains, but Bitcoin is typically classified as a permissionless blockchain. And the permissionless systems are systems in which the participants are not known, because, well, you don't need permission to participate, and they can change at all time. And for Bitcoin, this is because they want to support a decentralized and open cryptocurrency that can be maintained by anyone that wants to participate. And we see similar designs not only in Bitcoin, but also in Ethereum and other cryptocurrency projects. And these permissionless blockchains are interesting in the sense that they can quite easily scale to thousands of participants. But on the other hand, we also see that they have really low transaction processing throughputs and they have very high transaction latencies. So for high performance data processing, they are not the most optimal choice. The other option are permissioned blockchains, which we will focus on. And in permissioned blockchains, we assume that all participants are known beforehand. And this, well, one can defend this choice because data processing is typically done in a managed environment in which you know who the participants are, and even in a federated environment you typically know who the different parties are that you want to contribute to your data. And by choosing for permission blockchains, we also support different attack models than just the ones that cryptocurrencies have to deal with. And by doing so, this allows us to support ways to process transactions that have much lower latencies and can achieve much higher throughputs than one would see in Bitcoin or in Ethereum. Of course, it comes with a downside. By assuming that all participants are known, you're making it quite hard for changing the participants. Does that mean that permissionless blockchains are not relevant for this discussion, or our discussion? Well, not really, because we see with our work on permission blockchains that there are quite a lot of parallels with similar work on permissionless blockchains. But of course, the solutions to the problems we find are quite different than the solutions they find, just due to the difference in setting. Having answered why we want high performance resilient data processing and what it has to do with blockchains, we can next ask ourselves what we already have towards this goal. And the first thing we've already seen is that we have blockchains, and blockchains really operate based on consensus between replicas on which transactions to propose. So we also have already some consensus protocols to achieve this. And these consensus protocols like PBFT and Paxos and Proof of Work provide two main guarantees, namely they provide termination, by which we say that each non-faulty replica is able to decide on transactions to accept, and they provide non-divergence in the sense that if two non-faulty replicas decide on a transaction, then they must necessarily also decide on the same transaction, independent on how the malicious replicas behave. Of course, we do not operate consensus in a black box. We operate it in a system that deals with client transactions. So from that we get some more practical requirements, namely that the transactions we decide on must be valid. They must come from a client that requests them. We also want clients to be able to learn the outcome of their requests. So if a transactions get accepted, they get executed, and the client must learn what the result was. And we want clients to have some guarantee of service. So if a client has a transaction that it wants to be executed, it can request that to the system in a reliable manner. And we can visualize these guarantees in the following manner. We have a client. The client has a transaction. It sends it to the system. The system does consensus. And by some magic, all replicas will then learn of that transaction. They will execute it. They will report the outcome back to the client, and the client will get that response. Of course, besides consensus, we need a little bit more to arrive at a blockchain system, because consensus only decides a single transaction. In a blockchain system, we want to use consensus to maintain a consistent state among all replicas. So how do we do that? Well, we run consensus in rounds, and in every round we decide on one transaction. This gives us a list of transactions that is equivalent at all replicas, and then replicas maintain the state by executing these transactions. Of course, this will only work if all transactions are deterministic. So given that all replicas have the same initial state, if they execute a transaction, then they must always get the same final state. If that doesn't hold, of course, the state at each of the replicas will diverge after execution, which we do not want. Besides consensus, there are also, especially in theory, two variations of consensus that one typically sees, namely Byzantine broadcasts and interactive consistency. And the Byzantine broadcast problem basically changes the source of the transaction. It says there's not a client, but there's a general that has a transaction. And this general wants to broadcast it to all the other replicas. And if the general is correct, then all the other replicas will learn exactly the value that the general had. And otherwise, all other replicas will learn some value, but this value might not be the original value that the general has. And this is a slightly simpler problem than consensus. The other problem that one typically sees is interactive consistency, which is slightly more complex than consensus. And in interactive consistency, all replicas have a value, and after performing interactive consistency, all replicas learn of all the values of all the other replicas, and when the replica is correct, then all the other replicas will learn of its exact value, and otherwise they might learn of a bogus value if the replica is faulty. So in this example, we see that the third replica is faulty, so all other replicas will learn T1, T2, and T4 of replicas 1, 2, and 4, but they might learn an arbitrary value from replica 3. Besides consensus, we also have already seen that blockchains operate as fully replicated systems. And this means that we can apply the CAP theorem to specify what these systems can and cannot do. And the CAP theorem basically describes the properties of a fully replicated system in 3 categories. Such a system can provide consistency, which means that all participants have exactly the same state, exactly the same data. They can provide availability, so the system must be able to provide services in all the circumstances. Or they can provide partitioning, and partitioning means that if the network fails, if some replicas become unreachable, then the system can still operate or not. And the CAP theorem specifies that if you want to have these properties, then you need to choose 2 out of 2. You cannot provide 3, it's impossible. And this really limits what a blockchain can and cannot do. In practice, it's slightly different, because in practice we do not have absolute consistency or absolute availability or absolute partitioning resistance, but most systems use something in between, whereas the CAP theorem really speaks in absolutes. And to illustrate that, we directly look at blockchains. So if you look at a permissionless blockchain like Bitcoin or like Ethereum, they really focus on open membership. And open membership means that they can deal with clients being added to the system and removed at the system without further interference. And this basically also implies that they need to be able to deal with partitioning to some sense, while also always being able to provide availability. And in Bitcoin and in Ethereum, this comes at the cost of consistency, because we see that these systems do not provide consistency in the worst case. They can have forks of the blockchain, and this is especially the case if, for example, we have a very big Bitcoin network, the network gets split in half, and these two halves cannot communicate with each other, then each of these halves will just develop their own blockchain and never fall back to a single blockchain anymore. Permission systems, it's quite different. Permission systems really focus on consistency. It's all they care about. At all costs, all replicas will maintain the same data. And this comes at the price of both availability and partitioning. So what we see in these kind of systems is that they typically provide availability when communication is reliable. And they can deal with a little bit of partitioning. They can deal with some network failures as long as it only impacts a few replicas. And for the system, this basically means that these replicas are considered crashed at that point. But they cannot provide availability with a lot of network failures, and they cannot provide network failure resilience if they already have some crashes of replicas. But at all times, they have consistency. Besides these basic ingredients, there's quite a lot of other theory on consensus, and from that theory we can already quite easily conclude that consensus itself is really costly. Furthermore, we also have practical consensus algorithms like PBFT, which we will look into a bit more detail later on. And we have trample-proof ledgers that we already described. Of course, the exact details of such a ledger really depends on the consensus protocol used on the application and attack model. And we really described the Bitcoin model up till now. And we also have many cryptographic tools to make all of this work together. But if you look back at our original goals, we wanted high performance transaction processing, and we haven't provided anything yet that provides high performance. So that's really a point where we still have to do some work. Well, to continue, I already said we have a lot of theory and consensus. I will not go over all the details, but the summary is that practical consensus is rather limited. It cannot deal with asynchronous communication, which is the practical form of communication, because in practice, we don't know when messages will arrive. Messages can get delayed, they can get lost, they can get received out of order, especially if we deploy a system on a Geo-scale. And a real consensus system cannot operate in such an environment. They cannot provide both termination and non-divergence. So what we typically see is that practical systems say, okay, we're going to provide consistency, we're going to provide non-divergence, but as soon as the network becomes too unreliable, then we don't provide termination, we stop at that point. And we can only resume termination when communication becomes reliable again. We also see that practical consensus systems can deal with malicious behavior, but if we have F replicas that are malicious, then we need at least 3 times as many replicas in total to deal with these failures. And we also see that malicious behavior has a worst case impact on communication. So if we have F failures, then any consensus protocol that can deal with that needs to do at least F+1 phase of communication in the worst case. And in the best case, we see that the number of phases of communication is always lower bounded by the number of actual failures. And we also see it has that failure resilience has an impact on the amount of communication. So we see that communication is typically quadratic in the number of failures, and of course linear in the number of replicas, because of course we always need to broadcast our decisions to all replicas anyways. And it even has an impact on the type of networks we can operate in. And this in the sense that the network must be really, really connected. So in many practical systems we see that replicas communicate pairwise, but this is not required. But as soon as we remove a lot of replicas to have replicas, the network must still have connection between all remaining replicas. So it must be quite connected. In practice, it's not this extreme, like I already said. In practice, we do have asynchronous communication, and in these systems, we basically just provide termination only when communication is reliable. And in practice, we typically have something of a clique network or gossip network that operates like a clique network. We just saw quite some theory on what is possible in a consensus-based system and what is not. Now let's put it all in practice by looking at one of the more practical consensus protocols that we know, namely PBFT. Of course, PBFT is a bit of an old protocol, but we see that a lot of the concepts in PBFT are at the core of most of the modern protocols that are in use. So understanding PBFT is really the first step into understanding all these other protocols anyways. And PBFT operates via a very standard primary backup model. So in our replicated system, we assign one replica to be the primary, and this primary coordinates the consensus process by proposing transactions that all the other replicas need to replicate. Of course, because this primary can be faulty, because we're dealing with malicious behavior, the backups will receive these proposals and they will do some communication between themselves to verify the behavior of the primary. And in the normal case, this process is sufficient to get everything working. After the replication and verification, all the replicas will execute and they will inform the client of the result. And in the normal case of PBFT, this process consists of a few phases. First, the transaction is sent from the client to the primary. Then the primary proposes this request via pre-prepare message. And this pre-prepare message specifies the round in which the transaction needs to be executed. Then all replicas broadcast what they receive from the primary via prepare message. This allows replicas to determine whether they all got the same message or not. And if a replica determines that enough other replicas got the same as they did, namely n minus f other replicas got it, then they will commit to the proposal of the primary. And if they commit, they basically say, well, as long as this primary stays operational, in this round I will stick to the pre-prepare message that I received. And if a replica gets enough commit messages from other replicas confirming that they made the same decision as the replica itself, then the replica will execute and inform the client. And also here we use an n minus f threshold, which basically specifies the number of replicas minus the number of faulty replicas, because that is the maximum number of people that can agree in the worst case. In the normal case, if communication is reliable and the primary is good, then this will just always work, and there's no extra steps necessary to make the system work. But of course, we also need to deal with faulty behavior of the primary. And to illustrate this, well, consider here a primary. The primary is the faulty replica. We have three other replicas and we have two clients. The two clients send both the transactions to the primary, and the primary selects one of those transactions to send to one of the replicas, and the other two replicas, replicas 1 and 2, get the other transaction. And after the prepare phase, all replicas will just broadcast what they got, and some replicas will see that they got the same thing as some other replicas, whereas one replica, replica 3, determines that it got something that no one else got. So what will PBFT do in this case? Well, as I said, the commit phase will only continue if I get enough messages from other replicas that they got the same message. And this holds for replica 1 and 2 because they get from each other, but it does not hold for replica 3. For replica 3 will just stop, whereas replica 1 and 2 will say, okay, we're gonna commit to this first transaction. And after the commit phase, the same thing happens, and replica 1 and 2 will actually execute and inform the client. Of course, the primary is faulty, so the primary might even decide to also execute but another transaction and inform that client. And in PBFT, these two clients can determine whether they got an outcome yes or no by just counting how many replies they got. They know that there's one replica that can be faulty, so as long as they only get one message, they just ignore it. If they get more than one message, they say, okay, my transaction was accepted. So in this case, the first client is happy, whereas the second client knows that something is off. Of course, this only means that one of the clients knows that things are good. This does not yet mean that we solved all problems, because both the third replica doesn't know what to do, and the second client also just hasn't had anything executed yet. So PBFT also needs to deal with these kinds of behavior. And this is actually complicated, but at the core of all of this is that if two replicas will commit in a single round, then they have to guarantee to commit to the same message. So on the previous slide we saw that only replicas 1 and 2 both committed to the same value, and this property always holds as long as we have more than 3F replicas. which of course is, due to the theory, the lower bound that we have. To see why this is the case, well, we can just prove it. If I have a replica that commits to a message 1, then this replica only did so after receiving n-f prepare messages. So we can write all the senders of these messages as a green bulb. And some of those replicas might be faulty, but we know this number of faulty replicas is upper bounded by f. So n-2f of these senders of prepare messages are non-faulty. And we know that non-faulty replicas will only prepare a single message per round for the primary. So if we have two different messages that gets committed, then we know that we must have two sets of n-2f non-faulty replicas to be prepared for these different messages. But we also know that in total, of course, these two sets of non-faulty replicas for these two different messages must be at most n-f, because we have so many non-faulty replicas. This gives us a small issue, because of course we want this to hold, so we have these two sets, 2 times n-2f must be smaller than n-f. We can simplify that a little bit to 2 times f minus 4f must be smaller than n-f. And if we further simplify that, then we conclude that this can only happen to committed messages if we have less than 3f replicas, which we assumed is not the case. So PBFT guarantees that if two replicas commit to a message, then they must commit to the same message. But this only guarantees that we do not have some non-divergent divergent things going on. This doesn't solve all the other problems. And solving the other problems is actually really hard, because we have malicious behavior. And to illustrate this, here we have a primary that's faulty, and this primary decides to keep replica 3 in the dark by not sending it anything. What will replica 3 do? Well, at some point it decides, nothing happened, I think the primary is faulty, so it will send a message saying that the primary is faulty to all other replicas. Of course, this is one case that can happen. The other case that can happen is that the primary is good, but that the third replica is faulty, and it just pretends to be ignored. So in this case, the third replica does get a pre-prepare message, but still at some point it will say, well, I think the primary is faulty. And if you now compare these two cases from the perspective of replica 1 and 2, we see that they get exactly the same messages in both cases. So they cannot really determine what's going on. They know that some replica is faulty, either the primary or replica 3, but they don't know which one of the two is the case. So this really also complicates dealing with faulty behavior of the primary. So what PBFT does, it distinguishes between detectable primary failures and undetectable primary failures. And undetectable primary failures, these happen if the primary does something so bad that a lot of replicas say, okay, the primary is faulty. Why is this detectable? Well, if more than f replicas say that the primary is faulty, then I will get more than f of such messages. And as we know that there are only f faulty replicas, at least one of them must be from a non-faulty replica, and so we can conclude, okay, the primary is faulty and it's detected. And in this case, the primary needs to be replaced by a non-faulty primary. And to do that, PBFT uses a view change protocol. Of course, we already saw, first we need to detect that the primary is faulty. Then a replica needs to choose in this view change protocol a new primary. And this is typically just the next one. And this new primary must know what happened in the current of what the current primary did. So this new primary gets the current state of each of the replicas that says that the primary is faulty. And based on this current state, the new primary will determine what happened in this view and propose a new view in which it will propose its own request. And if I get such a new view message, then I switch to this view if it's valid. And otherwise, the new primary is faulty and we repeat the process. So to visualize this, here we have a faulty primary B with malicious, and two replicas already detected that. The new primary P prime and the replica 1. Both of them send out a view change request, and this view change request contains all the pre-prepared transactions that we need to keep of this view. The second replica, replica 2, did not detect any failure yet, but at some point it gets these two view change messages that determines, hey, there is only one faulty replica, so one of them must be from a good replica, and says, okay, then apparently the current primary is faulty. So he also sends his own view change, and this is an indirect detection. After this, the new primary has 3 view change messages, and this is enough for this new primary to propose a new view that contains each of these view change messages as a way to determine the state in which this new view starts. The old primary might have also skipped some rounds, and the new primary has to account for this by proposing no operations for these missing rounds. And after I get such a new view message, I just validate it and move to this new view by installing the state that has been proposed. And after that, the new primary can propose its new requests. Of course, this is all fine and dandy, but for PBFT to really work, we need a guarantee on this view change process. And namely, we need a guarantee that if a replica executes a transaction and informs a client, and the client learns of this, then this kind of proposals always need to be maintained. And if you really look at the guarantees that PBFT provides, and this boils down to guaranteeing that if a set of n-2f non-faulty replicas commit to a message, then we can get in a state in which a client can see execution. So in that case, the view change must recover that committed message in any way. So well, in PBFT this is quite easily maintained, and to prove this we can use a similar argument as for the non-divergence. Namely, we have n-2f non-faulty replicas that committed to a message, so they all have a pre-prepared certificate proving that. And in the view change message, n-f replicas provided their pre-prepared certificates. Of course, f of those might be from faulty replicas, so we don't base our state on that. But n-2f of these view change messages came from good replicas. And again, the set of people that committed and the set of people that committed provided the view change values must again overlap as long as we have sufficient replicas. So otherwise we get a contradiction with the number of replicas we have. So this really proves that PBFT in their view change process will always keep committed messages. Of course, it's not the whole story, because that's only how we deal with detected failures. We also need to deal with undetected failures. So if a primary only ignores a few replicas, then, well, we can't detect that failures. But luckily in that case, we have always sufficient replicas to allow these in the dark replicas to recover the state via a checkpoint protocol. And we can do these checkpoints even without the intervention of the primary, so we can recover from that. We've already seen with detected failures we do primary replacement, but that's not the whole story, because after I replace a primary, the new primary can also be faulty, so that also needs to be replaced. Unless we have f faulty replicas, in the worst case we can get a sequence of f of these view changes, and this of course correlates with the lower bound on the number of phases for any consensus protocol. Of course, the view change itself is a very costly process, because these view change messages are really big, and in practice we want to reduce that. A very easy way to do that is to not do view changes from the start, but view changes since the last checkpoint, and that's what most practical implementations do. Finally, we also need to deal with unreliable communication, because all the view change processes we describe really rely on messages being sent and received in all cases. If things go wrong and communication becomes unreliable, then we cannot rely on this. So what will happen in that case typically is that view changes will happen, they will fail, and they will only guaranteed to not fail as soon as communication becomes reliable again. And in this sense, like we said, consensus cannot happen in asynchronous systems, and in PBFT this means that if communication is too unreliable, we just won't make new decisions. We have to wait until communication becomes reliable again. Well, finally, we said that PBFT is a practical protocol, so we also want to know a little bit about its performance. And to do that, we can model its performance quite easily. So the first thing we look at here is a system deployed in a continental setting, say spread over North America. So between replicas, we have a bandwidth of 100 megabytes per second. We have transactions with a size of a kilobyte, whereas the prepare and commit messages exchanged are of a quarter of a kilobyte. And in this sense, we can quite easily determine what the maximum throughput of any system will be, because the primary will just send transactions and that's all what happens. And we know in such a system, of course, if we add replicas, the primary has to broadcast more data, so the transaction throughput will go down. This is our maximum. So the next question is, what would PBFT do? And if we execute PBFT just per round, we do a round and then we do the next round and then we do the next round, then we see that the throughput is really, really horrendously low. Of course, in a system with that is deployed in the continental United States, we will have a message delay of around 15 milliseconds. And with the 3 phases of PBFT, this means that every transaction takes around 40 to 50 milliseconds before it gets executed. So in the best case, we can do around 20 transactions per second, and that's not much. But of course, we can improve on that, and practical systems have to improve on that. So one of the improvements we typically see is that we do not propose a single transaction, but PBFT proposes a whole big set of transactions, say 256. This both saves us on, of course, transaction delay, but it also saves us on a lot of prepare and commit messages. And if we do this batching, then we see that the transaction throughput really, well, almost gets multiplied by a factor of 256. But still, batching does not really resolve transaction throughput if we have really high message delays. So to further improve on this, a lot of the PBFT implementations allow for out-of-order processing. And what does that mean? Well, basically the primary can just propose, and after it's proposed for this round, it can just directly propose for the next round, and the next round, and the next rounds. While in the meantime, replicas do the prepare and commit phases for this and for previous rounds. And this really allows the primary to use all of its bandwidth for proposing transactions. And if we do that, then we see that we already remove the reliance on a message delay for the performance. Still, we still have the overhead of the prepare and commit phase, and to further remove that, we can combine out-of-order processing, of course, with batching. And if we do that, we see that PBFT comes actually in most circumstances really close to the maximum throughput of any broadcast protocol. So in this sense, PBFT is actually a rather practical protocol. Of course, this is modeling. To achieve these types of performance in practice, we have to do quite a lot of system engineering. And my colleagues will later in the tutorial talk about how this system engineering is put into place to make this happen. Having looked at what techniques are already available for resilient data processing, the next question we ask is, where can we improve to really get high performance data processing? And what better place to look than at just databases and how they perform high performance data processing. And at the core of these systems is really the concept of scalability, in the sense that we need to be able to add resources to the system in such a way that we're also adding performance. And this is in contrast with the fully replicated nature of most blockchains, because in these systems we add resources in the form of replicas, and this will result in having less performance overall. Of course, databases provide scalability in several ways, and a very popular way is by using sharding. So instead of having a single system that manages all the data, sharding proposes to split up the data, for example by region, and each shard maintains its own data and processes its own transactions. So for example, we can have a shard with European data, and this shard can process all transactions that only affect European data. And at the same time, we can also have an American shard. Of course, life is not that easy, because there are also transactions that deal with both European and American data, and most shard systems provide for such transactions some coordination between the shards to be able to process these transactions. But in general, as a lot of transactions only affect a very small amount of data, we see that adding shards will typically add a lot of throughput by enabling parallel processing. It will also add storage capacity by assuring that each of the subparts of the system only have to store a small part of all the data. And another way in which database systems provide higher performance is by using role specialization. So instead of having a single system that manages the data, that performs read-only workloads, that performs analytics, machine learning, visualization, we split up the system into a single system that manages the data, that processes transactions, that update the data, and separate systems that are specialized towards analyzing the data, towards machine learning on the data, and towards visualizing the data. And these separate systems, as they are run completely separately from the management part, can even incorporate specialized hardware like GPUs or FPGAs to speed up things. And to enable such a design, of course, we need a way for the data system that manages the data to share all updates, to share the data with the read-only systems that do the analytics. And also in these kind of systems, we typically see that by adding new roles, by specializing roles, we can add parallel processing power and more performance. So what we want is to introduce these kinds of tools, sharding and role specialization, in the design of blockchain systems. But to do that, we need some new tools. And well, what kind of tools do we need? Well, we already know one thing. We know how to manage data, because we can do that with the blockchain itself, and that's resilient. So to enable sharding, what we can do is make each shard an independent blockchain, and that would require reliable communication between blockchains. It's not as easy as it sounds, because the blockchains themselves consist of replicas that can be faulty. So we need reliable communication between clusters in which individual components are faulty. And for role specialization, we can do a similar thing. We can make the storage system that manages the data a blockchain, whereas all the analytics is done by independent systems. And in that case, we need a reliable read-only way to update, send updates of the blockchain to these read-only workloads. And all these techniques have parallels in permissionless blockchains. So for communication between blockchains, permissionless blockchains have like relays and atomic swaps, whereas for getting read-only updates of a blockchains, permissionless systems provide light clients and stuff like that. And if you really look close to that, then we see that consensus, the main tool that we have, is really not of any use to provide this. So then the alternative is we make some new tools to provide this, and the first thing we look at is to enable sharding, for which we needed coordination between blockchains. And what we did is we formalized this problem, the problem of coordinating two clusters with Byzantine failures in each of the clusters, as the Byzantine cluster sending problem. And the sending problem can be formalized as follows. We have a cluster C1 and a cluster C2. C1 wants to send some value to cluster C2, and we want to do that in such a way that all replicas in the second cluster will receive this value. The replicas in the first cluster will get some confirmation that that value was received, and the replicas in the second cluster will only receive a value if the sending cluster actually agreed upon sending this value. So faulty replicas cannot impersonate or do something to convince the second cluster that a value was sent that they didn't agree on. And these are basically the main requirements one wants to have to provide reliable communication, even though some of the replicas that are involved in communication are faulty. And this sounds like not a too complex problem, and you can quite easily solve this problem by just having a broadcast protocol and using some counting arguments to deal with failures. But such a broadcast protocol has quite a lot of communication in it, because, well, it's quadratic communication. And especially if you do sharding on a global scale, whereby individual shards are local, but communication between shards is global, this is a really expensive approach, because well, communication on a global scale is typically several orders of magnitude more costly than on a local scale. So we want to improve on this. And to improve on this, what we looked at in our research is there a lower bound of cluster sanding? So is there a minimum amount of work that I always need to do? And is there a way to do this minimum amount? And to show that there is a lower bound, we look at this very simple example of two clusters, a big one and a small one. And the big one has 15 replicas, the small one 5. The big one 7 can be faulty and the small one 2. And in this setting I claim we need at least 40 messages to make cluster sanding happen. And to prove that, we're gonna do it, we're gonna show that with 30 messages we will always fail. So of course we want to reduce the amount of fails, reduce the amount of impact of faulty replicas. And to do so, we minimize the number of messages each replica sends and receives. So for the first 5 messages, this means we send from 5 replicas to 5 replicas. The second 5 messages, well, we only have 5 replicas in the receiving cluster, so the second 5 messages will go to replicas that already received the message. And the last 3 messages, we do the same. Of course, these are 30 messages sent in some way. Now we can look at which of these replicas that sent it and received crashed and which didn't. And in the second cluster we see that 3 replicas got 3 messages, whereas 2 replicas got 2 messages. Well, to knock out the maximum number of messages, we crash 2 of the 3 replicas that received 3 messages. And by doing so, we already lose 6 messages. Now if you count, you see that there are only 7 messages remaining, sent by 7 different replicas, so we can also crash all of those. And this means that by sending 30 messages in some way, we can crash sufficient replicas in the 2 clusters to make sure that nothing got sent even in the end, proving that we need at least 40 messages. Of course, this is a single example. What we can do is generalize this example to any size clusters. And there we see that, well, if we want to do cluster sanding, then we need to exchange a number of messages that is linear in the number of replicas. And to go in more specific for crash failures, we really see that there's the number of messages determined by the ratio between faulty replicas in one of the clusters and the non-faulty replicas in the smaller cluster. And of course, to deal with difference in sizes, we also have some remainder term that makes things a bit more complicated than that. Of course, having a lower bound doesn't mean anything if we don't have a protocol that can achieve this lower bound, an optimal protocol in that sense. And it turns out there's actually a protocol that has this optimal lower bound. And what this protocol does is basically follow the procedure that we showed in the example by picking the big cluster, partitioning its replicas in fragments that are the size of a small cluster, and let each fragment just one-on-one send. Well, we won't go into all the details of the protocol, but we will give a demonstration. So I have a big cluster that wants to send a value. It's decided on sending a value, for example, via consensus. And with these settings, the lower bound says that we need to send at least 6 messages. So the 6 replicas in this big cluster will send. And they will do that via global communication that is costly. And we'll see that the first 4 messages will go to distinct replicas and the second 2 messages will go to replicas already received messages. And now we can again play the game to let people crash, but now we see that even if we crash 3 replicas in the big cluster, 1 in the small cluster, we still have 1 message that got sent by a replica that is non-faulty, received by a replica that's non-faulty. And so in the second cluster, they can then internally rebroadcast this value to assure that everyone in the second replica will receive this value. And that's what we want. And this protocol is actually completely optimal. Now, of course, the next question is, can we do better? Because a linear amount of communication is still quite heavy. And a pessimistic answer to that is no, we can't do better, because we showed a lower bound. So what we do is already worst case optimal. But an optimistic version of the answer is yes, we can do better. Because if we just pick nodes at random, replicas at random, then we have a very high likelihood that these replicas are non-faulty. And we can instruct them to send between each other. Of course, high likelihood doesn't mean guarantees. So if you use such a probabilistic approach, then In the expected case, we might have to do several of these rounds, but still, in many cases you can show that we only need an expected number of 4 communication steps in total, which is much better than a linear amount. The details of this are upcoming and will be presented soon. The second new tool that we need to really enable high-performance resilient data processing is role specialization. And for role specialization, we already showed that we need a way for a blockchain to communicate all the decisions that it makes to read-only independent systems that process these updates. And we formalize this problem into the Byzantine learner problem, which we can just formalize as we have a blockchain that decides on a ledger, and we have a learner that wants to learn this ledger, and this learner has to be able to receive all transactions from the ledger, and the learner must also only receive those transactions, so it cannot be tricked into accepting other transactions. And in practice, of course, we want to minimize the amount of overall communication, and we want to load balancing all the sending the replicas in our blockchain do, so that none of them get overloaded. To solve this practical problem, we can use information dispersal algorithms. They come really in handy for this. And an information dispersal algorithm, what it does, you give it a very big value v of some size s, and it can break up this value into pieces of a much smaller size. And for our setting, we break it up in n pieces, one for each replica, such that the original value can be decoded from every set of n minus f pieces. So if I get a value from all the good replicas, then I can reconstruct the original value from that. What has been shown already in the 1989 is that information dispersal algorithm can be done in an optimal manner, in the sense that each of the individual pieces held by replicas has a size that is proportional to the number of pieces that we need to reconstruct the value. And if, in the sense that if we get all the pieces necessary to reconstruct the value, then these pieces have a size that is roughly equivalent to the size of the original value. Well, how do we put information dispersal in practice for solving the Byzantine learner problem? Well, we do that in the delayed replication algorithm. And this delayed replication algorithm basically says that we're going to take the ledger, break it up into n transactions per piece. These n transactions we will encode via IDA, and then we will send them to the learners. And to be able to deal with malicious behavior, we also include a checksum so that the learners can determine whether a piece was correct or not. And after a learner gets enough good pieces, n minus f, it can reconstruct the original ledger. And by using the information dispersal algorithm, we can show that each replica in our Byzantine cluster in our blockchain will only send an amount of data that's proportional to the number of replicas, which means that this is actually a scalable solution towards sending data. Furthermore, we see that the learners that receive the data will only receive an amount of data that is proportional to the size of the ledger and to the size of the number of transactions due to the checksums. Furthermore, let's give a small example. The delayed replication algorithm, of course, processes replicas of processed transactions in a number that is dependent on the number of replicas. So it first has to wait until a few decisions are made. And after that, it starts broadcasting, and each of the replicas will send their pieces to the learner. One of these pieces might actually be faulty, because there are faulty replicas, of course. So after the learner gets enough good pieces, it can reconstruct the original ledger, and it can do that even if some of the pieces are faulty. And after another 4 rounds, we repeat this process so that the learner will, with some delay, learn the ledger that has been accepted by our blockchain system. Of course, what we did not yet touch upon is how the learner will actually determine which pieces it gets are correct and which pieces are incorrect. And to do that, we included checksums. And the checksums we want to really use are based on Merkle-trees. And these Merkle-trees work as follows. Say we have 8 replicas. Each makes one piece, piece S0 to S7. And then we build a Merkle-tree out of that by taking the leaves, the hashes of these pieces, and taking intermediate nodes that are hashes of neighboring leaves. Now, how does the checksum then look? Well, what we do to determine the checksum for some piece, now piece S5, we take the path from the root to this piece, and then we take as checksum the root value and all neighboring values on this path. So how does this checksum work? Well, as I am going to get the root value for every single piece, I can determine by a majority vote what the root value is. And now given a single checksum for a single value, in this case S5, I can determine whether S5 is actually matching the checksum and the root. How do we do that? Well, we can calculate the hash value of S5, H5, and the checksum already provides us H4, so we can combine H4 and H5 to get H45. While the checksum also provided the neighbor of that, H67, we can combine that again to get the hash H4567. The checksum again provides the neighbor of that, and we can combine them to get the root. So if S5 was correct, then we get the root value that we want to get, and otherwise we get another root value, and we know that either the checksum or the piece is faulty, in which case the sender must be faulty. And this is actually a relatively cheap procedure, so this allows us to reduce the amount of computations one has to do to reconstruct a value using EDA. Applying this approach gives us a solution to the Byzantine learner problem via delayed replication that works as long as we have more than double of the replicas and half of them are faulty. Using this approach, we can guarantee that every learner will learn the ledger, and they will do so by getting a number of meshes that is proportional to the size of the ledger, and the size of which is also proportional to the size of the ledger. We also only have a number of decoding steps that is proportional to the size of the ledger, whereas all the replicas that participate in the process will only send an amount of data that is proportional to the size of the ledger and the number of replicas. And in this sense, we see that adding replicas to a blockchain will actually reduce the amount of communication we do to solve this problem. You know, of course, it will increase the amount of work we have to do consensus. So this problem will actually has a solution, even in a Byzantine setting, that is scalable, which is good. Furthermore, we can also apply the tools we used, information dispersal and stuff like that, to really reduce the complexity of blockchain systems by reducing their requirements for storage. And this is especially true for blockchain systems that only need to maintain a view of the data and don't really need the full ledger, because the full ledger in a lot of systems is actually only used for recovery. And in that case, we can assign replicas to not store the full ledger, but only store the EDA pieces. And then other replicas can learn from these EDA pieces and reconstruct the original ledger. And this can make storage a lot more scalable in blockchain systems. So I've provided an introduction on permission blockchains and how permission blockchains can be used to provide high performance resilience. Let's look at some concluding remarks. What we've seen is that we need a very extensive toolbox to really get resilient data processing with high performance. And one of the main tools we already have is consensus, and in permission systems this is provided by PBFT or by Paxos. And in permissionless systems this is primarily proof of work, but we also need more. For example, to enable sharding, we're going to need cross-blockchain communication. In permission systems that we studied, this can be solved via cluster sending. Permissionless systems, we have relays for this and atomic swaps. We're also going to need ways to enable read-only participation. And in permission systems, we can do that via Byzantine learning. Whereas permissionless systems, this can be done via light clients. But looking at all of this, we already can conclude that high performance resilience data processing, our main goal, is actually not that far removed from reality, and we are actually quite close to achieving that. If you want to learn more of that, some of the things we talked about, like cluster sending and Byzantine learning, have already been published. And we've also published at VLDB some work on geo-aware consensus with very high performance. And more of our work can be found on our website of our labs and of our Resilient DB platform that we're working on.
Hello everyone, welcome to session 2 of this tutorial. In the session 1, we looked at theoretical aspects of PBFT, and Jelle gave us a good idea about how different consensus protocols work, what is the basic theory. Now we'll dive deep into some of the existing consensus protocols and propose ideas for the new ones. We know at the core of any blockchain application is a Byzantine fault-tolerant consensus protocol, which ensures that all the replicas agree on the same order. The very first protocol to do this practically was PBFT, which was presented at OSDI 99. And what does PBFT say? Well, PBFT can tolerate up to F failures in a system of 3F plus 1 replicas. It requires 3 phases, of which 2 necessitate quadratic communication complexity. Safety is always guaranteed in PBFT, while liveness is only guaranteed in the periods of partial synchrony. Now let us have a look at how PBFT works. In this system, we'll work with 4 replicas, that is n equal to 4, and we assume one of the replicas is bad. Now here we have the primary, and a client sends a transaction T to the primary. The primary creates a pre-prepare message. He attaches a sequence number, and then he sends this pre-prepare message to all the other replicas. Once a replica gets a pre-prepare message from the primary, it understands that primary wants to order this request, and it agrees to support this order by sending a prepare message. Once a replica gets 2F prepare messages, basically it gets a guarantee that a majority of non-faulty replicas are also ready to order this request, or they got the same request from the primary. At this point in time, each replica is ready to commit this request, and they do so by sending a commit message. Once a replica gets 2F plus 1 commit messages, now it is sure that there were at least a majority of replicas who were ready to execute this request. So this replica goes ahead and executes the request, and they reply to the client. Now, if you'll have a look, here the prepare and commit phases, they both require quadratic communication complexity because the messages are being transferred between all the replicas. Now, it is possible that the primary is bad, and that primary may not send messages to everyone. It might skip some messages. In that case, PBFT introduces something called as a view change protocol, where if the current primary is bad, all the replicas can agree together and then they can elect a new primary. So how does it work? Let us assume all the replicas detect that the current primary was bad. Well, they start by sending a view change message to each other. Basically, this view change message includes the history of existing transactions which were completed from the last checkpoint. Because since the checkpoint has already completed, the last checkpoint already had information of previous requests. So from the last checkpoint, all the requests which were not completed are enclosed in this view change message, and this is sent to all of the replicas. Once the new primary, it receives a view change request from 2F plus 1 people, it knows that there are a majority of non-faulty replicas who find this current primary is bad and they want to replace it. So this new primary creates a state, and he checks that now it's got a majority, so he sends this new view message to everyone else. Once everyone gets a new view message, they update their state, they move to the next state, and they're now ready to basically enter the new view. So this was PBFT. And in PBFT, we saw there's quadratic communication complexity, and we saw that if the primary is bad, there's a way to replace the primary, which itself is actually expensive. Now, since PBFT, there have been several works which have tried to improve its performance. One of the famous works in this direction was a speculative consensus protocol called as ZZWA. ZZWA was presented in SOS for 2007. And how does it work? Well, Ziziva says that it is possible to use speculation to achieve consensus in a single phase. Basically, Ziziva guarantees that if there are no failures, then it can achieve a communication protocol which is linear in complexity and helps achieve consensus among the replicas. Now, Ziziva requires good clients. Why? Because it's assuming consensus in single phase, so now the replicas are aware of the state of the replicas. So they require clients who can basically order these requests. And a client can only order this request once it gets responses from all the replicas, basically all the 3f+1 replicas. Note that Ziziva's good case only works if there is no failure. A single crash failure is enough to impact its throughput, and we'll see it later how. Interestingly, Ziziva has been proven unsafe, but just for the sake of completeness and to explain its design for the future protocols, we are going to discuss Ziziva. So how does Ziziva works in a good case? We are again assuming a system where there are 4 replicas, and there's a client. And the client sends this request T to the primary. Now, like PBFT, the primary will attach a sequence number, and he will now forward this request to all the other replicas. In PBFT, if we had an idea that at this point in time, replicas had no clue whether primary was behaving good or bad, but they agreed to support the primary's request by sending a prepare message. And then once they got prepare message from majority of replicas, they agreed to move to the next round, basically to check whether they can commit the request or not. In Ziziva, all of that will not happen. At this very point of time, the replicas will speculate to execute the request, and then they will basically reply to the client. Now, client at this point in time needs to check whether there were responses from 3f+1 messages. Basically, in this very specific system, client needs to wait for responses from all the replicas. And once it gets response from all the replicas, it's assured that yeah, the request got completed successfully. Note that none of the replicas at this point of time are aware about whether each one of them have the same state or not. Now, if this is a scenario, that means if one replica fails or something bad happens, then the system's throughput should fail. How does it happen in Ziziva? Well, we'll assume there is one replica. We're calling it a Byzantine replica, but it can be a simple replica which just crashes. We follow the same thing. There's a pre-prepared message by the primary. All the replicas execute and reply to the client. But note that one replica hasn't replied. The client only gets 3f responses. Now, in this case, client will timeout. And now client will switch to something called a slow path protocol. So Ziziva is a twin path protocol, which says that in the good case, you follow the fast path. All the replicas execute the request and reply to the client. But if client does not get enough number of responses, then it starts the slow path. So how does slow path work? Well, now client has to create a certificate. It basically compiles all the messages it gets from different replicas. And then what it does is that it sends that commit certificate to all the other replicas. And once every replica receives the commit certificate, it has to send an acknowledgement back to the client that, hey, we got the state, we are aware of the state, and you can proceed. Notice that this client timeout could be expensive because one, client is waiting for 3f+1 responses. And if it gets any number of responses, it does not know when to end. So there's a timeout period it has to wait for. And that could lead to severe degradation in throughput, which we will show later. So Ziziva was one protocol. We know that Ziziva has been shown to be unsafe. And the same authors that proved Ziziva is unsafe designed a new protocol called SBFT. Basically, SBFT is a safer alternative to Ziziva. SBFT tries to achieve consensus in the linear fashion, same as ZZ1. And how does it do so? It does that by employing threshold signatures. Well, how do threshold signatures work? Threshold signatures employ the asymmetric key cryptography, where there's a public key and a set of pair of private keys. So every replica creates its own share, and the primary, once it gets shares from majority of replicas, it combines those shares into a threshold signature. Now, each replica who receives this threshold signature can verify that that threshold signature was made from a combination of threshold shares. So how does SBFT works? Well, when we'll see SBFTs working, we'll see that it basically has similar phases as PBFT. And what it basically does is it splits each phase of PBFT into two linear phases. SBFT also requires twin paths, a fast path and a slow path. Basically, the fast path works till the time there are no failures, and the slow path only switches when there are failures. SBFT also introduces a notion of collectors and executors. Now, let us look at SBFT's normal case. There are several executions. As I said, in the fault-free scenario, SBFT requires that there are no failures. Or SBFT authors basically proposed a way where they said that SBFT can handle C greater than 0 failures. Basically, if it has C number of collectors, then it can handle C plus 1 crash failures, only if the system has n equal to 3f plus 2c plus 1 number of replicas. In specific, if C is greater than 0, then it can handle failures. But if C is equal to 0, then the system has basically 3f plus 1 replicas, which is same as saying it cannot handle any failures. Let us look at how SBFT works. In this system, we are again having 4 replicas, but now some of them have designated jobs. There's a primary replica, there's a collector, there's an executor. Client sends his request to the primary. Primary creates a pre-prepare message. He assigns a sequence number. He sends that to all of the replicas. Now, at this point in time, each replica will basically create a threshold share. Basically, they'll use their own private key to create a share. And once they create that share, they will now send that share to the collector. At this point of time, collector needs to check whether it got share from a majority of replicas. Once collector gets shares from at least 2f plus 1 good replicas, it knows that it is in the good shape. It creates a threshold signature and it sends the threshold signature to all the other replicas. At this very point of time, once all the replicas get a threshold share, they know the state is stable and they're ready to execute the transaction. But instead, SBFT says something interesting. It says that at this point in time, all the replicas again create a threshold share, basically which is a threshold share created on top of the threshold signature sent by the collector, and then they send that to the executor. Once executor gets threshold shares from a majority of replica, at this point in time, executor is ready to execute the transaction and he replies to the client. Also, executor sends this proof to all the other replicas. So if you have a look, there are similar phases as PBFT. That is what is happening. Although the system has become now linear because of the usage of threshold signature. So we saw that SBFT basically helps to linearize the consensus and it removes a failure of ZZ1. But SBFT, PBFT, or any existing protocol, they still require view change. If the primary is bad, the primary has to be replaced. So there was a recent protocol which is called as hot stuff, and which basically removes the notion of view change. Basically, hot stuff also linearizes like PBFT, like SBFT, but what it promotes is something called as leaderless consensus. It says that how about we frequently change primary? And what is the benefit of frequent changing primary is that no one primary can actually be handling massive number of requests, and then the view change process may not be cumbersome. Similar to SBFT, it requires threshold signature, but due to requiring frequent changes of primary, it infers something called a sequential consensus or sequential processing. Hot stuff comes in two variants. There's a basic variant, which says that primary can be switched at the end of each consensus. And there's changed variant, which says that we can employ sort of a pipelining, and each phase of the consensus is run by a distinct primary. Now, let us have a look at the flow of hot stuff. In a very simple sense, we'll assume there is a client who sends a request, but we'll try to see how hot stuff phases progress. So, assume there was one phase before this thing, and that phase got completed. So the now next primary has to be selected. This new primary is selected by everyone sending a view change. This view change request is nothing, just a hash of the previous request. Then the new primary, if it has a client request, it takes that request and it proposes on the top of the existing request by sending a proposal. And then what rest follows is similar to what PBFT does, or even SBFT. Everyone sends a prepare vote. Then once everyone gets a prepare vote, basically at this point in time, primary collects all those threshold shares given by all the replicas at this point in time. It creates a threshold signature and he sends that threshold signature to all the other replicas. Once every replica gets a threshold signature, it verifies it. It again creates a threshold share and sends it to the primary. Now at this point in time, primary again combines these signatures and he wants to confirm that all the replicas are at the same state. Note that this confirming is important in hot stuff compared to other protocols because hot stuff requires changing primary in every phase. And that's what is being done here. So there's an extra phase here. And once this is done, now hot stuff completes because primary has a full copy of the data. And every replica is aware that everyone has got the same set of requests. So they're ready to move forward. This is the basic version of hot stuff. In the chained version of hot stuff, at each of these points, a new primary is getting selected. Basically, at this point, the first primary got selected, then you sent a proposal, everyone the prepare message, and now we basically pipeline. So instead of sending these threshold signatures to the same primary, they might send it to the new primary. Let's assume this is the new primary. They send it to this guy. And then this guy will attach another proposal, and then he will propagated that to other replicas. Basically, in the chained version, it will still require latency of 4 phases, but at the end of every phase, a new primary is selected and a new request is being proposed. Now, why did I say in the beginning that hot stuff forces sequential processing? Because if you see, at the end of each consensus, hot stuff is changing primary. That means no single primary can continuously send many requests, which is possible in protocols like PBFT or SBFT. Because PBFT and SBFT allow that one primary can send a lot of requests. He can just assign sequence number. He does not need to wait for previous request to complete consensus before he can send the next request. While this is sort of enforced in hot stuff because each primary can only propose a request or a batch of requests, but he cannot send multiple batches or multiple at the same time. So apart from these protocols, there are some other designs which we will not go into detail, but let me just talk about them. So there's a set of protocols which say that, hey, how about we increase the number of replicas? So right now we assume n is equal to 3f plus 1. And we already saw that SBFT requires 2c more replicas to do this thing. While it's a protocol like QU which says that, hey, how about we have 5f plus 1 replicas? Instead we have that many number of replicas, then QU says that we can actually achieve linear consensus. if there is no failures, which is fair enough, but the number of replicas being acquired are too high. Then there are some set of protocols which say that, how about we use trusted components? Basically, these protocols suggest that every replica has a trusted component which helps in preventing primary from equivocating. And if you do that, then what helps is that the total number of replicas required in the system are less and fewer communications required. And every replica gets a guarantee that the primary can no longer cheat. That is good, but the whole system's reliance now depends on a trusted component. And if the trusted component fails, the system can sort of fail. So now we'll switch gears and we'll present some of the designs that we have thought about in this Byzantine fault tolerance space. In our first design, we'll talk about a protocol which we call as proof of execution. And the whole idea of proof of execution is basically to achieve linear consensus like SBFT or hot stuff or ZZIVA, but do it in fewer phases. As we saw, SBFT requires same number of phases as PBFT. It basically splits each phase using threshold signature. And hot stuff, it requires more phases, but it allows frequent primary change. In PoE, we want to reduce the number of phases and still ensure the protocol is linear. We want to use the notion of speculative execution, which was proposed by ZZIVA. And we want to ensure how can we do things fast. That we do through the use of out-of-order message processing. Further, we want to ensure there's no dependence on clients or we don't require any trusted component. And definitely we should not rely on any twin path design. We should not have a protocol where there is a fast path and suddenly either the client timeouts or collector timeouts or replica time, someone timeout, and then we switch to the slow path. We don't want that. So we thought of doing a simple theoretical comparison of what PoE does in comparison to other protocols. And this is how it works. As you can see, PoE requires the least number of phases compared to all other protocols. And it has a very low message complexity. It provides as high reliance as other protocols, a number of failures. And moreover, PoE has a distinction. Although right now we'll show a design of PoE that requires threshold signatures, PoE can be designed without using threshold signatures also. In the paper, we have proposed a design which uses max. So we basically call PoE a protocol which is signature agnostic. So let me express the design of PoE. We are again having a system of 4 replicas, and we assume at least one of them can be bad. How does it work? Client again sends his request to the primary. The primary creates a pre-prepared message, and then the primary sends that to all the replicas. When a replica gets a pre-prepared message from the primary, it validates the client request. It agrees to support primary's request by sending a prepare message. Now, at this point of time, in PBFT, all the replicas were sending prepare message to every other replica. In SBFT, because it uses threshold signature, every replica created a threshold share, and it sent its share to the collector. We don't have a notion of collector executor. We can have a similar design. But what we do is that we make every replica send their threshold share to the primary. Now, in SBFT, what happens is that once primary or collector gets these threshold shares, he combines them into a threshold signature. And then what it does, it started another phase. In PoE, primary will still combine, and he will send all that combined signatures to all the replicas. All the replicas will now execute the request, and they will simply reply to the client. So where did that extra phase go? Because after this point in time, SBFT required all the replicas to basically again create another threshold share, and then send it to the executor so that executor can execute and reply to the client. Or PBFT required an extra phase. Why don't we require so? Well, we allowed our replicas to do speculative execution at this point of time. So our replicas have partial guarantee here. In comparison to Ziziva, where all the replicas execute the request at this very point of time, they had no clue what all other replicas knew about. In PoE, replicas have a little bit more guarantee. They have a signature, a threshold signature, which is a proof that majority of replicas were supporting it, and then they executed. Now it is possible at this point of time that some replica could not execute, or the primary was malicious. In that case, PoE allows replica to roll back the request. So by using rollbacks, we are able to save an extra phase. Note that rollbacks are not required every time. They're only required if primary is malicious, and it may not be required by everyone, it might be only required by a few set of replicas. So let's look at a scenario where what happens if the primary is bad. So how does a replica come to know a primary is bad? Well, a replica will come to know a primary is bad in PoE once it does not get a threshold share. If it does not get a threshold share, it will not be able to execute the request and will not be able to reply to the client. In such a case, it will say, hey, my primary is bad, something has to be done. And that is what is being done. Every replica basically claims that primary is bad, something has to be done. So now the new primary, he waits for messages from majority of people. If majority of people are ready to cry that, hey, primary is bad, they know like, okay, the new primary knows that I got a majority of people saying the primary is bad. Now I need to move to the next state. Note an interesting thing. It is possible that this new primary and replica one, they detected the previous primary as bad before this guy detected. Hence, this guy can join later. Once he gets messages from F+1 people saying that the existing primary is bad, he will also join the mutiny. And he will say, let's throw away the existing primary. The new primary is ready. He gets messages from majority of people. And what he does is that he just proposes the next stage. He basically combines what state everyone is saying, finds a state which majority of people support, and then he sends that message to everyone else. And then everyone else, once they get this new view message from the new primary, they're happy to move to the next stage. This is interesting to note here that this state, what has to be decided is decided by the new primary. So it is possible that this replica 2 might have thought about some request to be executed while no other replicas thought about it. So in such a sense, this replica needs to do rollback at this point of time. So how does PoE perform in comparison to other protocols? Because that is what is interest to us, knowing. Well, we perform a very simple experiment where we try to see is that how PoE does under failures. Because failures are very interesting to us because it is at that point in time where we can show that protocols like SBFT and Ziziva, which are fast and linear, but they require this twin path scenario. And this twin path basically leads to severe reduction in throughput. So we scale PoE up to 91 replicas. And as you can see, throughput required by SBFT is quite low, and by Ziziva and hot stuff is also quite low. First, let's talk about hot stuff. Why is hot stuff performing low? Because as we said, it enforces sequential processing. Only one primary can propose at any point of time. Why is Ziziva's throughput so low? Well, if there's even one single failure, well, the client will continue waiting for 3f+1 and he cannot proceed. And once only timeouts, then he can do something more. For a similar reason, even SBFT's throughput is low, but SBFT is more reliant because it can handle a little bit more crash failures. So PoE clearly outperforms other protocols. and it scales very well. And it also achieves quite low latency. The throughput, the latency of hot stuff and ZZ were already low because they're already not processing any requests. The system does not have any load. They can easily process. As you can see for other protocols, PO is very well. So POA gave us an idea that it is possible to basically make PBFT faster without requiring on a twin path system or without relying on a client or any trusted component. But we wanted to do more. Our whole idea was, why is only one person doing all the work? Well, blockchain talks about democracy and decentralization. Democracy says give all the replicas the power. So we want to make in RCC on this principle resident consequence concurrency control, we want to ensure that every replica has the power to become the primary. We want to introduce the notion of parallelism. Basically, why just run one instance of BFT protocol? Can we have multiple instances? And then we want to have decentralized, because right now we want to say that, hey, if the primary is bad, then the primary has to be replaced and everything just stops. Can there be always a set of requests which are getting ordered? And that is what RCC does. It avoids that whole system is depending on just one replica. It ensures that malicious primary can no longer throttle the system throughput. It tries to ensure that malicious primaries are not the bottleneck of the system, because even replacing malicious primaries causes a reduction for throughput of the system. So now we'll present how does resilient concurrency control or RCC work. In this presentation, we'll show RCC's design with just one protocol, PBFT. But RCC can be employed with several other BFT protocols like ZZWA, SBFT, and POE. The key idea which RCC requires is it requires a protocol to be primary backup. Basically, it should be led by a primary. RCC basically works in three stages. It expects as input a BFT protocol, and it asks how many instances do you want to run parallel. So Z are the number of instances I want to run parallel. And what does RCC does? It runs Z parallel BFT instances on each replica. Now, once each replica has run consensus on its Z of the instances, they create a global order of all the requests, and then they will execute this request in the order and reply to the client. Note something very interesting. There's a loop back here. Basically, ordering and execution are independently running of the consensus. So the Z instances can independently continue consensus on their set of requests while ordering and execution is happening in parallel. Now, let us present design of RCC with a very simple diagram. So we'll assume RCC with PBFT, and in this diagram, we'll assume each replica has two parallel instances. So we have two clients and we have 4 replicas. In each replica, there are 2 instances. Now, as we have 2 instances in each replica, so we'll assume there are 2 primaries. Let's assume first primary is here, and let's assume the second primary is somewhere here. So how does RCC progresses? Well, both the clients send the request to their individual primaries. So now this client is sending the request to the primary for instance 1. And this client is sending the request to primary for instance 2. In RCC, we require a minimal requirement, that is no primary should be having more than one instance control. So once primary receive this request from the client, well, they follow the PBFT protocol. They send the pre-prepare message. Next is the prepare stage. And then finally, it's the commit stage. What happens next is very interesting, because at this point in time, each replica has commit messages from majority of other replicas for both the instances. So basically each replica has the full state or full information about other requests, which is basically all the set of requests. Now, at this point in time, RCC requires each replica to create a global order. A simple way to create a global order is just assume a linear ordering. For example, this primary's ID is 1, this primary's ID is 2. So we'll say that request of 1 should be ordered before request of 2. We can also employ very complex schemes where we can ensure that none of the replicas knew at the start what the order should be, and they can only determine the order at the end of the consensus. Such a scheme we present in the paper, and we request you to read the draft for more details. Now, once all the replica have decided an order for the request, and this order should be deterministic. That is what we require in the protocol, that everyone can determine the same order. They all execute in that order, and then they reply to the respective client. And that is it. That is how RCC works. But RCC introduces a notion of multiple primaries. And as soon as we have notion of multiple primaries, it is very much possible that two primaries or two or more primaries could be malicious and they can collude. And note that this situation is very distinct from existing BFT protocols, because in existing BFT protocols, we had one bad primary. And to remove that, we had a view-chain protocol. We saw the view-chain protocol in PoE, we saw the view-chain protocol in PBFT, and all the other protocols also follow similar stuff. But now we have multiple bad primaries. And we'll show a scenario that if there are multiple bad primaries, they can prevent liveness. And a way to solve this thing is basically through state exchange. But before we go into that direction, let's try to at least illustrate what the problem is. So here we'll assume three sets. We'll assume a set A, which is a set of good replicas. There are F good replicas here in A. There's another set B of F replicas, which are also good. And finally, there is one good replica C. So the total count of good replicas in this thing is 2F plus 1. That is as expected. And we'll assume there are F bad replicas. We'll assume a system where there are two malicious primaries, that is P1 and P2, and the remaining malicious replicas are F minus 2. Now, P1, he proposed a request M1 to only A and C. And P2 colludes with P1. He only proposes the request M2 to B and C, set of replicas. Note that replicas in A did not get request M2, while replicas in B did not get request M1. Only replica in C got both M1 and M2. Now, why is this interesting? Only this replica in C will be able to complete all the phases of the consensus of RCC, and then he will be able to execute the request and reply to the client. Now, these malicious replicas, they are working well with the primary, these malicious primaries. So they'll also execute all the requests, and they'll also send replies to the client. Note in this scenario, client got F plus 1 responses. He's happy, he went home. But there are two F replicas who could not even do anything. Replicas in A are stuck. They don't know what should we do. They didn't get M2. Replicas in B are similarly stuck for M1. We can easily show if the number of bad primaries are more than 2, they can be a scenario where not a single replica executes any request. So how do we solve this problem? Well, a way to solve this problem is requiring state exchange. But when do we do state exchange? Well, we require our replicas to detect this problem. So once they detect that there are at least 2F set of replicas, basically if there are at least F plus 1 replicas who are complaining there are 2 bad primaries, at least 2 bad primaries, then they start this optimistic recovery through state exchange. More details about this can be found in the paper. So now, how does RCC performs in comparison to other protocols? Well, we did 3 testing. So as we said, RCC allows Z number of instances, and this value of Z could vary. We said that we'll have 3 cases where Z is equal to 3. Basically, you can easily divide 3 F plus replicas into 3 sets of F plus 1. Or we can have Z equal to F plus 1, which ensures there will be at least one good primary. Or you can have all the replicas as primary at the same point in time. And what we want to illustrate here is that these are the plots for RCC and these are the other protocols. And these experiments are done under failure, just one failure. And you can clearly see how much is the performance difference. RCC is getting 26 times higher performance compared to protocols like Hotstuff, something. So this is where I conclude about RCC. And I'll be happy to take any questions for POA or RCC or any other protocols. Apart from that, I will now ask Sajjad to switch.
Hi. Up to here, Suyash and Jelle talked about blockchain and BFT protocols. They introduced some traditional BFT protocols like PBFT and Ziziva, and they also introduced some of the modern ones like POE, RCC, and hot stuff. However, all these previous works are missing something. What if the replicas and participants in the system are in geographically distant locations? What if the communication between these replicas is expensive? The most important promise of blockchain is to bring decentralization. And decentralization happens when the nodes and replicas in the system are in different continents in the world. We think that the underlying BFT consensus protocol should be topology aware and understand and have an intuition of where these nodes are located. The global scale resilient blockchain fabric is also part of Proceedings of VLDB 2020, and it's also going to be presented in the blockchain session. In this figure, we tried to give you an idea of how global scale Byzantine fault tolerance protocol works. As you can see, we divided nodes and replicas into different continents. We have nodes in America, Africa, Asia, and Australia. Each of those big, large rectangles on top and down is a clusters that have 3 F+1 nodes. Each of those clusters are responsible to order transactions in their own cluster, and they also responsible to transfer those blocks to the other clusters, so everybody in the system have the same view of the ledger. And as you can see in the lower rectangle that's showing the replicas have the blocks of red, green, and blue, and all the clusters. Now, what is GeoBFT protocol? GeoBFT is a topology-aware protocol which groups replicas into the clusters, and each cluster is responsible to order the transactions of its own clients in parallel and independently. It has 3 phases. The first phase is local replication. Each cluster runs a PBFT to locally replicate and certify the client's request. After locally replicating a request, the primary of cluster needs to share the certified client request with a commit certificate with the other clusters, so everybody have the actual request to execute and apply to their ledger. And the last phase would be ordering and execution. Once all the clusters have the results of all consensuses of the clusters, they can execute and apply those transactions to their ledgers. So in this slide, we will be going through the workflow of GeoBFT and how it's working. We demonstrate GeoBFT with 2 clusters. The upper one is C1 and the lower one is C2. Each of them have their own primary, own clients, and own replicas. At the first part, the client will send their request to the primary of their cluster. The primary will start running a PBFT consensus, each one on their own client request. There will be prepare, and commit phase in those PBFT consensus instances. And after that, the primary needs to share the client request and the certificate that this request has been ordered in that cluster with the other cluster. As you can see, the primary will send the commit certificate and the client request to F+1 nodes in all other clusters. That would be our reliable intercluster communication that has been proved that is working and the presence of malicious primary, it will detect and replace that primary. After this step, there would be local sharing, because not everyone in all cluster receiving commit certificates from the primary. There would be local sharing phase, and after that, they can execute and send reply back to the client. So we conclude GeoBFT with the following takeaways. GeoBFT ensures common ordering across different clusters with linear intercluster communication. The primary replica at each cluster will send a secure commit certificate to F+1 replica of every other cluster to make sure that every cluster will have the commit certificate and the client request of all the other clusters. These certificates guarantee the common ordering for execution in all clusters. In the presence of malicious primary, or if the primary prevents or sends an invalid commit certificate to other clusters, our secure way of intercluster communication will detect and will change the primary by remove view change subprotocol. In this slide, we will be showing the results of experiments on resilient DB and some modern and traditional BFT protocols. As you can see, GeoBFT or resilient DB scales well enough with increasing the number of clusters or regions. The throughput of resilient DB is increasing by adding the number of regions, because by adding regions, the parallelism of GeoBFT is also increased, and the throughput will also increase. Hot stuff, Steward, Ziziva, and PBFT are not performing well enough in the Geo-scale environment. As you can see, resilient DB or GeoBFT has a throughput of around 60K transactions per second with 6 regions. Each region has 4 nodes in it. Up to now, we talked about a new BFT protocol that tried to scale well enough in the Geo-scale environment. In the next part, we are going to talk about how to design a permission blockchain platform and how to implement and design it. The permission blockchain through the looking glass architectural and implementation lessons learned is also part of Proceedings of Forwardings IEEE ICDCS 2020. Why should somebody choose resilient DB or our architectural and implementation? So Bitcoin and Ethereum offers low throughput, around 10 transactions per second. Existing permission blockchain databases have low throughput, around 20K per second. Everybody in the community blames BFT consensus protocol as an expensive part of each permission blockchain system. They usually overlook the system design and implementation of the permission blockchain system. Resilient DB adopts a well-researched database and system practices. So with all the shortcomings and drawbacks of existing permission blockchain protocol, we have so many dilemmas and design choices in front of us in designing a permission blockchain system. For example, where to use single-threaded monolithic design, what we are going to do with the successive phases of consensus, how execution and ordering will be integrated together. Do we need a strict ordering or not? What about off-chain and on-chain memory management? And finally, which scheme for cryptographic signatures or hashing schemes we need to use. So the whole purpose of this design is to show that if a well-crafted system based on classic BFT protocol can outperform a modern BFT protocol. As you can see in this image, the green one is ZZiva and the brown one is ResilientDB, which is using PBFT. As you can see, PBFT is outperforming ZZiva with high margin, although it has three phases of quadratic communication. However, ZZiva has just one round of linear communication. It means that designing and implementing a permission blockchain system is important. So how is the architecture of ResilientDB? In this slide, we are showing a high-level abstract view of our ResilientDB. As you can see, there is a secure layer which have signing tools, signing and hashing toolkits. We have a consensus layer with BFT consensus in it, threads, worker threads, batching threads, and all in the middle. And we have queues, message queues, work queues that are communicating with network with input and output threads. And beneath all of these layers, we have a storage layer, which is the actual blockchain or the distributed ledger is being maintained alongside the metadata of all those transactions and smart contracts in our permission blockchain architecture. So if we zoom in to our consensus part in the architecture, we will see some things like this. As you can see, the left part is the network. We have input threads there. All those input threads are receiving messages from different nodes and putting them into the message queues. We have batch creation thread, worker thread, and checkpoint thread. In PBFT and traditional BFT protocols, checkpointing is a way to garbage collect the messages and the consensus. Checkpoint, there's a specific thread for doing that. Worker thread is the main thread which is processing the messages of BFT consensus protocol like commit message, pre-prepare message, and prepare message. And the batch creation threads are processing client messages and batching them and sending them as a whole as a pre-prepare message to all other nodes. The batch creation thread is just in primary nodes. And finally, we have the execute thread, which is executing the transaction and the smart contract. As you can see, there is just one execute thread, and that's because we need to execute every transaction in a linearizable order. And at the end, we have output thread and output queues, which the results of works of worker thread will be put in those queues, and the output thread will send them through the network to the other nodes. So from now on, we are going to investigate different insights on designing a blockchain system. The first one would be comparing multi-threaded pipeline games with single-threaded ones. We are going to compare two different protocols called PBFT and ZZiva. As I explained before, ZZiva has just one round of linear communication. However, PBFT has two rounds of n-squared communication with one round of linear communication. The number of E and B in the legend of this figure is the number of execution and batching threads. We are going to show how parallelizing and pipelining tasks across execution and batching thread will help to get better performance. The dashed lines are ZZiva and the solid lines are PBFT. The first one is PBFT and ZZiva with 0 execution thread and 0 batching thread, which means just one worker thread. As you can see, they do not scale enough well, and with 32 nodes, their throughput becomes less than 40K per second. So by adding one execution thread to both ZZIVA and PBFT, it adds up to one execution thread and one worker thread. As you can see, the trend is the same. The ZZIVA is still better than PBFT, and both ZZIVA and PBFT with one execution thread is better than ZZIVA and PBFT without execution thread. So the performance increased when we add just one execution thread, and we parallelize the execution and make them independent as worker thread. So the next one would be adding batching thread. Once we add one batching thread to ZZIVA and PBFT, the performance significantly increased. And as you can see, both PBFT and ZZIVA's throughput with one batching thread with 4 and 8 node has a huge margin without huge margin compared to PBFT and ZZIVA without batching thread. However, again, when it scales up to 32 nodes, it is still not noticeable the performance increase. But when we add one more batching thread to the PBFT and ZZIVA, the throughput of both of them will significantly increase even with 32 nodes. And this shows that having multiple batching thread, execution thread, and worker thread can increase the performance and the throughput from 40K to even 80K. It means 2 times better in 32 nodes. And with 4 nodes, the throughput from 70K, it went up to 200K. So now let's move on to the next insight. The next insight would be how batching would help increasing throughput and reducing the latency. Is it good or not? Previous work had different ideas on batching. Some of them were claiming that batching is good. Some of them were claiming batching would lead to the poor performance. As you can see in these two figures, the left one is the throughput and the right one is the latency. With the different size of with a different number of transactions per batch, the throughput is increasing up to one optimal point, and after that the throughput starts getting decreased. So we found out that the 1000 transaction per batch is the optimal batch size, and it shows that batching will help the throughput. And as you can see, the throughput from 1 or 2K per second, it increased to 150K throughput per second. And it means batching has very huge impact on the throughput and even latency. And as you can see, the latency of 30 seconds with decreased to even less than a second for 1000 transaction per batch. So the next one is to investigate how memory or storage can affect the performance of the permission blockchain system. We are comparing in-memory storage and SQLite storage. As you can see, in-memory storage is significantly better than SQLite because the access time, the access cost and time during the consensus is so low. So it shows that using on-memory storage would help permission blockchain system get better performance, get higher throughput and lower latency. So the next insight would be the number of clients. How the number of clients will affect the throughput or the latency of a blockchain system. As you can see, the number of clients is important because with 4, as you can see in the left figure, the throughput of a blockchain system with 4 clients is around 60K per second, and it is increased by a factor of 2 when we go to 16 clients. And as you can see, after some points, the throughput is not changing at all because it reaches to the saturation point. However, the latency is increasing linearly. Why? That's because when you are sending, you are having too many clients, the client requests would be queued in the primary, and the average latency would increase because the queuing time will increase and the total average of latency of client's transaction will again increase. So this would be our last insight. We have, I think, 6 more ones in the paper. If you're interested, you can take a look at it. Now let's move on to our next part of the tutorial, which is a hands-on tutorial on Resilient DB codebase, which we're going to show you how you can adjust and configure your own blockchain system and even implement your own BFT protocol inside. So how to run the Resilient DB? The first step is to go to our GitHub page and clone the repository to get the source code. Resilient DB has different ways to run. The first one is a Docker. What is Docker? Docker is an open source project that automates the deployment of software applications inside the container. It allows you to run the distributed program on one machine if you don't have access to Google Cloud or Amazon AWS or these things. It simulates the lightweight virtual machines. The performance numbers you will be getting would not be the actual one because all the machines are being simulated on one single machine. So in order to run Resilient DB with Docker, there is a script for a demo that you can use. It calls Resilient DB Docker. It accepts 2 parameters, the number of clients and the number of replicas. All the other parameters are inside the config file that I'm going to explain later on in this tutorial. But first, in order to see a demo of how Resilient DB would be run, let's see how Resilient DB Docker script works. So I have the Resilient DB directory here. I have cloned the repository. You can see the Resilient DB Docker script there. I will be running Resilient DB Docker script with 8 replicas and 3 clients as it accepts 2 parameters. When I hit the enter, it will first create a Docker compose file, which is supposed to create Docker containers. And after that, it will bring up those containers. After that, it will find the IPs of those machines. It will create ifconfig file and post all the IPs in that config file. The config file will be creating here. All the default setting will be used. And then the code will be compiled. As you can see here, the code is being compiled. It's still getting compiled. In Resilient DB, every dependency is being added to the binary and linked to them statically because we wanted Resilient DB to be run completely independent from its environment. And as you can see, once the compiling gets finished, it will be distribute those binaries for replicas and clients to those containers, and then run the Resilient DB on those replicas and clients. The running time would have 1 minute of warm up and 2 minutes of running. In the first 1 minute, nothing will be measured, neither throughput nor latency. Everything is happening. The clients are sending transaction, the primary will sending pre-prepare message, and all the stages of consensus is happening, but no measurement and statistics is happening. This is warm-up time that is supposed to fill the pipeline, fill the queues, allocate the message pools, transaction pools, and all those stuff. And in the second and third minute, everything will be measured. The throughput, the latency, how much idle time worker threads does have, for example, how many transaction is being processed, and all those stuff. After running it, there's a script which tries to collect the results from each node and each container and gather them and shows you a summary. After it got finished, I will show the summary and also each node independently. The running time and all this stuff also are adjustable in the config file that I'm going to explain later in these slides. Resilient DB uses nanomessage, gmalloc, and boost library. These are the libraries that we are using in our queuing, our worker thread, our batching thread, and our execution and transport layer. So the execution has finished and we have the summary of results here. And as you can see, we have the throughput of 5K in first eight nodes, and the throughput of each client is around 1800, which adds up to 5400 in all nodes. The average latency is 10 seconds, and I'm saying these numbers are not accurate because all these 11 nodes are being simulated on just one machine, which is my laptop, that has just 4 core, and each of those machines are using more than 8 threads, and that's over using one machine. Once you run this on actual Google Cloud or on Amazon AWS, the numbers would be accurate. Here you can see the idle time of each thread. The first one is the worker thread, the second and third are batching thread, the fourth one is checkpointing thread, and the last one is execution thread. And as you can see, in non-primary node, the idle time is 0, which means they haven't used their batching thread because they are not primary. Just the first one, which is primary, is using its batching threads, and the execution thread and checkpointing thread. And here is the summary of how much memory they have been used, and here is the average throughput and the average latency. So we saw how Resilient DB Docker script worked. That script just meant to show a demo of Resilient DB and how it works. I again explain here the steps. It was first removing the old containers, creating new ones, create IP address setting, install dependencies, compiling the code, running binary files, and gather the results and showing the results. I also explained what those results mean and how you can interpret those things: throughput, latency, the worker threads, idleness, execution, batching, and checkpointing threads. Up to here, we talked about those demo ones, the script, the Docker script, and all those stuff. From now on, we want to look a little bit deeper into Resilient DB. There is a config file.h in the root directory of repository that has a lot of parameters to configure. Here I have a very limited and selected ones to explain to what extent the Resilient DB is configurable. For example, the node count, the thread counts, the thread counts is a number of batching threads, client node counts, max transaction if light. What is max transaction if light? Each client will send their request to the primary, and they will not overwhelm the primary with their request. They will send a constant amount. For example, if max transaction if light is 2000, they will send 2000 requests and wait to get the first response. Once they get a response for that, they will send another. So the processing transaction for one client, the concurrent transactions that is happening for one client, is set up with max transaction in flight parameter. The done timer is the time that the experiment goes on. For example, the default is 2 minutes. The batch thread and batch size is the parameters to set the batch setting. The transaction per checkpoint is how frequent the garbage collector works, and the checkpointing subprotocols will start after this amount of transactions. The use crypto is a Boolean variable that allows you to turn off and turn off the crypto, the signing, the hashing, and message authentication code. And the last two parameters are set in the config file.h in order to set which signature scheme do you want to use, ED2 or CMAC and AES. There are hundreds of these parameters in the config file.h. Because of the shortage of time, we haven't mentioned here. And if you are interested, you can take a look at the config file.h. There's documented file there. You can understand all those parameters by yourself. Now we are going to show the next way of running ResilientDB, which is through our web interface and web GUI. So here is the admin dashboard of ResilientDB, which has a lot of parameters to set and run ResilientDB. The first parameter is number of nodes. For example, I will set it to 10. The number of clients, for example, 4. We have regions. You can select where your node would be located in Google Cloud or Amazon AWS. You can use US, Europe, Asia, India. You can have the different permutation of these regions to select. The next parameter would be benchmarking, whether you want to use simple YCSP benchmarking system or banking smart contracts. You also are able to add your own smart contracts to the ResilientDB, which we'll be explaining later on in this presentation. The next thing would be selecting whether do you want IO thread, worker thread, execution thread, checkpointing, and all these pipelining and thread setting in this environment. The next one would be the storage, whether you want to be SQLite, LevelDB, or in-memory. I will be using in-memory to get a better performance. The next one would be signatures. Which signature scheme do you want to use? I will be using CMAC, for example. The next one would be hash scheme, whether you want to use SHA-3 or SHA-256. The max transaction in flight, I explained it before, the number of transactions that each client can have concurrently. The consensus protocol, you can use Ziziva or Practical Byzantine Fault Tolerant or PBFT, and you can also implement and add your own consensus protocol here. The next one would be the request per transaction. Each transaction in YCSP has a number of operation. This number is that number of operation. For example, if I set it to 10, the number of operations per transaction in YCSP benchmark would be 10. The pipelining, you can disable or enable the whole pipelining system. The message size or payload would be the dummy payload on the client request, and also pre-prepare messages, which are the actual transaction that are going to be sent in the consensus protocol. And the last one is batch size. How large do you want your batch size to be? You can choose from 1, I think, to 20,000. Now I will just be using 100. Once you set up all your parameters in the web dashboard, you will be clicking run, and it will say the ResilientDB started successfully. And you can see the logs here online. For example, it has created a config file, and now it is compiling the code. And after code gets completely and successfully compiled, ResilientDB will be run with the number of nodes that you have set it up in the above setting. And after that, there will be warm-up time. After 1 minute of warm-up time, the actual running will happen. But before warm-up time, no measurement will happen. Because of that, we will wait till warm-up finishes so we can click on the data analytics and see the results of our experiment online. So let's wait for warm-up to be finished, then we will be going to data analytics part. After the warm-up finishes, the actual running will be happening, and now we can click on the data analytics, and the statistics and analysis will be shown in the next tab. As you can see, we have one window per node. We have R1 through R10, which are the nodes that we have set it up in the setting. And we have also the 4 clients that we choose to have, for example, client 1 to client 4. You can look at the throughput of all of them here. For example, the R10 has a throughput of 83K here. Here it was 95K. It's getting balanced. And you can get the throughput of all nodes here. For example, here node R8 has the throughput of 88K. The node R7 has the throughput of 82K, and so on. And the clients has less throughput because the sum of the throughput of all clients will be the throughput of the nodes. As you can see here, each client has around 20K throughput. With 4 clients, it will add up to around 80K throughput, which are happening in the nodes. For example, if you can see R2 has throughput around 81K. And yes. In the next part, we are going to go over PBFT, practical Byzantine fault tolerance, and see how PBFT fits to our resilient DB and how one can create or implement their own BFT protocol. The first part is the main function. We have 2 main functions, one for client and one for server. In those main functions, the queues are being initialized, the transport layer is being initialized, the stats layer is being initialized, and all threads are being created. This is the place you usually do not need to touch in order to implement a new protocol, and that's just where this code is being started. As we explained before, every BFT protocol or permission blockchain system is based on messages. So everything that is happening between nodes are sending messages and processing messages. We have a transport directory and we have a system directory. In the transport directory, all messages have been defined there. You can create your own message and you can take a look at messages that are there. What functions do they have? They usually, all of them are inherited from a message class that has few methods and attributes like validate function or sign function or message size and these kinds of properties. If you want to create your own a message for your own protocol, you just need to inherit from the message class and implement those functions for your message. Corresponds to every message, there would be a function to process that message. So if you add a new message in the transport directory, you need to implement a process of that message in the worker thread.cpp file. So if you create a message, you will be creating a process function for that message in worker thread. The worker thread was the main function in the consensus layer to process and decide on what's going on and what is going to happen after processing each message. For example, when a client sends a message to the primary, the process client message will be triggered in the primary, that I will be going over it in the next slides. So let's go over the PBFT flow and see what's happening there. The first step is the client to send a message to the primary. This sending message is happening in the client thread. In the client thread, client creates a message and send it to the primary. And we are going to start what's happening in the primary. As you can see, there's a process client batch message. There's a process client batch function in the worker thread PBFT. So if you look at that function, the flow is so easy. The function validates and verifies that the message has been arrived from a valid client. It's been signed carefully. And after that, it will create a digest, assign a sequence number to it, and create batch request and send batch request or pre-prepare messages in PBFT to everybody in the system. The next part, in this part, as you can see, the primary gets the client request, send it to everybody. Now everybody needs to process that pre-prepare message or batch request. So here is a process batch function. Batch message is the same pre-prepare message in the PBFT. In this part, the actual client message has been sent with a sequence number from the primary to everybody. So everybody in every node, the process batch function will be triggered. If you look at this function is again so simple. It just again create a digest of client message and see whether it's the valid digest that has been came from primary, verifies and validate the signature of the message to see whether this message is being received from a faulty primary or not. Otherwise, it will create transactions from that batch request message and then create prepare message and broadcast those prepare message to everybody in the system. The sending prepare message is the second phase of PBFT protocol. So after pre-prepare message or batch request message, it comes to prepare and commit messages. As you can see in the flow of PBFT, we have prepare and commit messages. So once nodes in the system gets pre-prepare message or batch request, they will send pre-prepare and commit messages. Corresponds to each of these messages, there's a process for these ones. For example, there's a process PBFT prepare message and process PBFT commit message. In those messages, the only thing is happening is just counting them, validating them, and once it's reached to 2f+1, they will once it reaches to 2f+1 prepare message, they will send a commit message, and once it reaches to 2f+1 commit messages, they will send an internal execute message to the execution thread for a transaction to be executed. As you can see, all the flow of PBFT is happening here through the messages and processing those messages. And you can do whatever you want here with the transactions and with the messages that you are sending and receiving. Sending and receiving messages are through the IO thread that I will be explaining later in these slides. After a replica receives 2f+1 commit message, they will send an internal execute message to the execution thread, and that execution thread will try to execute that transaction. PBFT requires linearizable order on transactions. So if a transaction number X is going to be executed, the transaction number X-1 has to be executed previously. Otherwise, it will wait for that instance of consensus to be done. So the X-1 to be executed, and then X can execute its own transaction. and go forward. After executing the transaction, a new message needs to be sent to the client as a reply back. In the process execute function, after successfully executing the transaction, this message is being it will be created and will be sent to the owner of the transaction, which is the client. So that was the whole workflow of PBFT and how it works. Now we have other elements in ResilientDB. We want you to have an understanding about the important one. One of the important ones is work queue. Work queues are the queues for each thread. For example, execution thread has its own work queue. So when somebody wants to send an internal execute message, it will put the internal execute message to the execute work queue. Or if a input thread receives a prepare or commit message, it will put those messages to the work queue of the worker thread to be processed. These work queues are lock-free, so they will be a spin lock on the queue to they will use atomic cast to avoid race condition and to have concurrency on the same queues for different threads, because the multiple input and output thread will be putting and picking messages from these queues. The last important part are IO thread and transport layers. IO threads are very simple. They just have a while true loop, and they ask transport layer to receive a message from the socket. Transport layer is using a nanomessage next generation library, which opens a pair of socket on each node. So each pair of nodes has their own open sockets through the whole experiment. And if, for example, the number of input and output threads are 3, each pair of nodes have 3 open sockets throughout the experiment for each other. And I think that sums up to our whole ResilientDB hands-on tutorial. If you have any question, you're more than welcome, and thank you.